We have seen the AdaBoost algorithm, which is a particular version of tree boosting for exponential loss in a binary classification context. We will now see the boosting algorithm in the general case. Let's go back to our original problem. Consider a dataset Dn, or set H of weak predictors, or loss L, and a starting function f0. For each iteration, we seek to optimize H and alpha, where alpha is a real parameter and H is an element of our predictors set. The final prediction is given by a weighted combination of the elementary predictors added to the initial predictor, i.e. f0 plus the sum for t equal 1 to big T of alpha t ht in regression, and the sign of this expression in classification. At each step, we look for the predictor ht, which, when added to the aggregated predictor f with a weight alpha t, leads to the largest risk reduction. The optimization described in equation 4 is complex because of the potentially infinite nature of the space H and the joint nature of the optimization in H and alpha. In order to simplify this optimization step, we will rewrite the quantity in equation 4. For any observation I, the loss between the true label yi and the prediction provided by the aggregated predictor f t-1 xi plus alpha h xi can be rewritten to the first order as presented in equation 5. This approximation is valid only if alpha h xi is small enough. Under this assumption, note that the right-hand term in equation 5 decomposes into two parts. The first does not depend on either alpha or h, and the second involves the derivative of the loss with respect to the second variable, evaluated at f t-1 xi, the prediction provided by the current aggregated predictor at xi. Using the fact that the first term of 5 does not depend on either of the two quantities to be optimized, we can inject 5 into 4 and obtain the simplified optimization problem presented in 6, where, without loss of generality, we have assumed that alpha is positive. If this is not the case, we can consider minus alpha and minus h as replacement for alpha and h, which leaves the optimization problem unchanged. With this first-order approximation, we can rewrite the boosting algorithm by decomposing the joint optimization into two successive optimizations. First, we want to find ht, minimizing the quantity we derived earlier in equation 4, and then find alpha t, minimizing the loss defined earlier in equation 5. Unfortunately, the optimization of the criteria is always complex, since the optimization space in 4 is potentially infinite. Notice that to optimize equation 4, we want to obtain a value of h xi that is close to minus the partial derivative of L with respect to z, where z equal f t-1 of xi. We can therefore approach this optimization problem by looking for a predictor ht that is close enough to this negative derivative for each observation xi, yi. This amounts to solving the problem described in equation 4. One way to find ht, approximating this quantity, is to train a predictor on data that are composed of input xi and output minus the partial derivative of L with respect to z, where z equal f t-1 xi. For each I, let us compute the previous quantity minus the derivative of the loss and store this quantity in an object denoted Ri. We then train a predictor on the dataset consisting of the xi as input and the Ri as output. The inputs are the same as in the initial set, but the outputs are replaced by the negative derivatives Ri. In this way, we learn a predictor ht that approximates the Ri, which was our goal. We have thus made successive approximations to solve an exact optimization problem using a learning algorithm. We must now find an algorithm to solve the optimization problem in alpha presented in equation 5. This problem is simpler than the optimization in predictor h because the parameter alpha is real. We can therefore use a generic backtracking line search procedure to find an approximate solution to this optimization problem. Such procedures work iteratively, starting with a large value of alpha, multiplied by a factor less than 1 at each iteration, until a value of alpha is identified that leads to a decrease in the objective function. Finally, we will also add the additional parameter new. At each iteration, instead of updating the aggregated predictor ft via the formula ft equal ft-1 plus alpha t ht, we will update it via the formula ft equal ft-1 plus new alpha t ht. The parameter new is set between 0 and 1 and allows to regularize the boosting procedure. Indeed, if an individual predictor would perfectly predict the dataset, it would be chosen during the first iteration. It would then be very difficult, if not impossible, depending on the loss used, to find predictors in the following iterations, allowing to improve the aggregated predictor. The boosting algorithm would strongly overfit in this case. To avoid that, after only a few iterations the training error is very low, we add the parameter new, which allows reducing the performance gain of each iteration and thus the overfitting phenomenon. The boosting procedure is therefore summarized as follows. Based on a dataset Dn, a learning procedure H, for example a decision tree algorithm, and a loss L, we initialize our aggregated predictor. In practice, this initialization is the optimal constant, allowing to minimize the risk corresponding to the chosen loss. It is, for example, the average of yi for the quadratic loss. For each iteration, we compute the residuals, i.e. minus the partial derivative of the loss with respect to the second variable, evaluated in the prediction of the aggregated predictor of the previous iteration. We then train a predictor with the procedure H on the original dataset for which the labels are replaced by the residuals. We then find a predictor HT, then a parameter alpha t by backtracking line search, and update our aggregated predictor. The procedure is repeated until we obtain the final predictor. To understand this algorithm, let's study the special case of quadratic loss in regression. Note that, in this case, the residuals take the form 2 times yi minus ft minus 1 xi, i.e. 2 times the difference between the true label and the prediction of the aggregated predictor of step t minus 1. In other words, in the case of regression problem with quadratic loss, at each step, we look for the individual predictor targeting the residuals of the aggregated predictor from the previous iteration. We seek to predict the difference between the prediction of the aggregated predictor of the previous iteration and the reality in order to improve the predictor in question. This is exactly how the general boosting procedure was presented in the first part, and this is what justifies the name of residuals for the elements Ri.